All right. So we're going to get into our next chapter section thing called ions and ionic bonding, and it has all to do with the electrons in an atom. We're going to be focusing more on those. Do you guys remember? Excuse me, here. You guys remember the charge of electrons?
Negative.
Negative, that's right. That's really important as we will learn about how the charges affected things. You remember how much mass an electron has?
Zero.
Zero mass, that's right. Good job. So when we change these things, it's not going to be changing the mass of anything. The protons and the neutrons control all that, and we're not really that focused on them. So you can see how this one, you know how we were drawing all the protons and neutrons, now it's just kind of simplified, and we'll simplify that even more just by putting, like if this is chlorine, we might just put Cl here in the middle. Okay, we know it's a chlorine amount of protons and neutrons. Now we're focused on the electrons in great detail. So we're especially focused on valence electrons. So this is like one of the first vocab words here. Valence electrons are the electrons in the outermost shell. So the ones in this third layer out here. Can someone tell me how many electrons you see in that outside layer?
7.
7. That's right. Good. So that's all that we need to count and worry about. All those other dots in there, those are full shells. Those are already conquered and moved on past. The atom doesn't really care about them too much as long as they're still there. So in this first shell, like always, we have 2. The second shell we can hold up to 8, as you can see there. And then in the third shell, also up to 8. We probably won't mess with any shells above that because then they turn to like 18 and 36 and all sorts of crazy stuff. And we're not worried about that. I never had to do it even in my college chemistry classes, so you guys should be good too. So, we can see lithium, 1 valence electron. Fluorine has 7 valence electrons, and aluminum has 3 valence electrons. Doesn't matter all the other numbers, don't need to worry about them, just that outside layer. Okay? So, here comes our question, what is an ion? That's one of the big things here. The topic was ions and ionic bonding. An ion is an atom or a molecule with a net electric charge due to the loss or gain of 1 or more electrons. What's all that mean? So if it gains or loses an electron, which is a negative charge, right? It's going to either become more positive or negative. If it lost an electron, do you think that would make it positive or negative? What do you think, Danielle?
Negative.
Negative. You would think that because it lost something, right? But because it's losing a negative charge, it's becoming positive. Like if you lose a negative part of your life, you're going to be happier, right? If you lost homework, that'd be better, right?
I sucked on my drum.
If you lost math class, maybe that would be better, right?
Yeah.
But no, so losing negative charges, losing electrons is going to make something positive, and gaining those negative charges is going to make it negative. So we're going to learn if it's going to gain or lose electrons. That just depends on things in the periodic table. So here's how an ion forms. Whenever an electron is lost, one goes away, well, we're left with this. How many valence electrons does this have? How many electrons in the outer layer does it have?
No.
0 in what used to be its outer layer, right? Yeah, so you can call that 0 valent, or you can go back to the layer before it, and it's a full shell, so it's good with that. Same thing with sodium, okay, if it loses an electron, it loses a negative charge. Now it's a positive ion with a full outer shell, and it's good. Once an atom has a full shell, it's good to go. It doesn't want to change any more than that. One thing on the next slide anyway. Here we go. So the octet rule. This is that all atoms tend to form bonds that consist of 8 electrons or a full outer shell. So we've looked at ones that are losing electrons, just like this sodium is here. It doesn't just lose it to space or wherever, it goes somewhere. Where do you think it's going to tend to go? If you look at this picture.
Fluorine.
Oh,
To another atom or another element. In this case, it's fluorine, yeah. So fluorine has 7 valence electrons. It wants 8, right? It wants to have that full outer shell of 8 electrons. So fluorine atom in its pure form or whatever is always looking to gain an electron. And the sodium is always looking to lose an electron. So when they find each other in nature, it's like a match made in heaven, right? It's like, please, someone take this electron. And fluorine's like, anybody will take any electron. And they finally get linked up and get rid of its electrons. They're happy. This will form what's called an ionic bond. What happens to this sodium when it loses one negative charge? What's its charge become?
Positive.
If it loses a negative charge, it becomes positive. What does the fluorine become if it gains a negative charge?
Negative.
Negative, that's right. So think of positive and negative like magnets now. What do the opposite ends of magnets do?
Attract.
The exact same thing with this. These are magnetically attracted to each other after this because of their positive and negative charges. So we're going to start figuring out how to do this on our own. We're going to use the Lewis dot structure to show this and to draw this because it's the easiest way to do it. And we like easy, right? So, for the number of valence electrons on the outside of an element, we're going to put a dot. So I'm going to have to show you a couple examples to make sure you start to understand this. It's not real hard, but it can be a little confusing at first. So, lithium. You can see right there it has one dot outside of it, right? Let me show you how I can figure that out. Alright, if I drew a lithium the old way that we used to draw it, the Bohr model way, the really detailed way, okay, I got all my protons, all my neutrons, I gotta match my electrons with my positive charges, right? So 1, 2 in the first shell, and I need one more to match that. So how many valence electrons do I have here?
4.
One electron in the outside layer. So I can draw this as Li, one dot. Let's do another one, so you can see what I'm talking about. Carbon. If I draw carbon, alright, and now I start to draw its layers. 1, 2, 1, 2, 3, 4. How many outside layer electrons does it have?
4.
4. I'm going to draw it as 1, 2, 3, 4. So Lewis dot structure is using dots around the chemical symbol to represent the valence electrons. This is a really common form that is used in science whenever talking about how elements bond and stuff like that. So you need to be able to see, okay, I have 4 dots around it. That means that we have 4 valence electrons around it. Thankfully, we don't have to draw it every time to know. There's an easier way. We click on the slide, please. Thank you. So this is how we know how many there are. Everything in, let's look at the pink box first, okay? This is the number of valence electrons of everything in this row. Everything in this row has 1 valence electron. Everything in this row has 2 valence electrons. 3, 4, 5, 6, 7, 8. Why didn't I do all these?
Cause they're nobody.
Because they're weirdos, more like it. Okay,
Yeah.
they can have bizarre numbers of valence electrons in their outer layers. Same with that the other box down there that I can completely cut off. You don't need to worry about those for this. Those don't really participate in this type of bonding as often anyway. Yeah, we're going to be focused on learning from these rows. Octet rule, 8. There's 8
8.
rows. It's all going to keep coming back to this number 8 for electrons. Okay, that's really our focus. So, Isaiah,
Mm-hmm.
can you think of any element in any of these layers or rows here? One where you know where it's at? Hydrogen. It's up here in the top left, right? So how many valence electrons should I draw when I draw the Lewis dot structure? 1, that's right. TJ, can you think of any other elements other than hydrogen that you know where they're at on the periodic table?
Helium.
Helium, where's it at?
The
I should have not highlighted that one green because it is the only one that is an exception to this rule. Because it does not have 8 valence electrons. But, can you guys figure out how many it has? How many dots do you think it would have?
4.
4? That's a good guess, because that's its atomic mass, right? What do you think, Ethan?
1.
1? Almost. Okay, it's going to
2?
end up with 2. And let me draw it and let me show you. Alright? It'll make sense. So I told you that octet rule is whenever an element has 8 outer electrons in this full shell, that's when it's happy, right? Well, helium, it has, I don't know why I drew HE. It has 2 protons, 2 neutrons, that gets the atomic mass of 4, that's what you're thinking of. So how many electrons is this going to have if it has 2 positive charges?
9.
2 negative charges. Is that outer shell full now? It has a full outer shell, and that's actually why helium is over here. All of these on this side have a full outer shell. Now for helium, that means only 2.
2.
It's a little bit different, okay? It's good to go with 2 because that's the first shell. It is the exception to this rule. I shouldn't have highlighted that, that's my fault. But the rest of them, they all have the exact number that they're in that row. First row all have 1. Second row all have 2, 3, 4, 5, 6, 7, 8. Now let's look at this black box I put underneath it. Charge that forms ions. Okay? What did we say lithium's going to tend to do with its electron?
Give it away.
It's going to tend to give it away. It wants to give away its negative charge. Okay, it's giving away this negative charge. So it's going to become positive. Lithium is right here. It's going to become positive 1. Next one over, beryllium. Be 1, 2. Guess what it's going to want to do? It's going to want to give away both of these. It's going to want to give away 2. So its charge is then going to be, so you can draw this as plus plus or positive 2, whatever you want. I'm not going to get picky about that. Some people want it drawn as all the plus signs. Alright, so let's look at this as we go across, shall we? In the first row, we're going to get rid of their 1 electron and become positive 1. These ones are going to get rid of 2 electrons, become positive 2. 3 electrons, positive 3. What happens here at this 4th row?
Don't know.
Plus or minus 4.
It takes away or takes 4.
Well, let's draw carbon. Well, we actually already have carbon right here. It has 4 electrons in its outer shell. It wants a full outer shell. Do you think it'd be easier to gain 4 electrons or lose 4 electrons?
Game.
It's not really easier either way. So it could gain them, or it could lose them. It just depends on the situation. Ones in this row don't commonly participate in this type of bonding. It's harder to lose or gain 4 electrons than it is to gain 1 electron. So let's keep going over now. Okay, this one could gain or lose 4. Then we get over here. This one can gain 3 electrons. 2 electrons, 1 electron. And these,
0 electrons.
they don't tend to bond at all, ever. These guys over here, the noble gases, they're too cool to bond with everybody else. They all have full shells.
They're gases.
They're all gases, yep.
I don't think they can bond with their gases.
Well, a lot of these over here are gases, and they definitely can bond. The ones that tend to bond the most is row 7 and row 1, because it's easiest to gain or lose just 1 electron. That's all they want to do. This is a really important slide for this. So when we do the thing, if you start feeling confused, go grab a Chromebook, pull this up. I put it on Google Classroom, the whole notes, but you can pull this up while you're doing this, and it might help you, okay? Just to see these positives and negatives that form. I think it'll start to make sense once you get into it, though.
Nope.
I think it will.
Nope.
Alright, so, ionic bonds. Bonds that form from the positive or negative charges associated with transfer of electrons. I think this is the last slide. So we can see here, sodium is giving up 1 to chlorine. It forms sodium with a full outer shell and a chlorine with a full outer shell. Has a positive charge, this has a negative charge. Let's do a different one. So, let me think here. Let's do beryllium, which has 2, and oxygen, which is in the 6th row. So it has 6. 1, 2, 3, 4, 5, and 6. Can anybody see where this is going to go?
Nope.
Take a second then. Look at this.
One of them is gonna give their electrons away.
Yeah, which one do you think is going to give away their electrons?
Oxygen.
Do you think that oxygen is going to give away all 6?
No.
No, none of them give away 6. That's what's the easier option? Yeah, this guy's going to give away 2. Right there. You see how that can be paired up?
Mm-hmm.
And right there. That can be paired up. We're always looking for these nice little pairs of electrons. Now, this one has 8, and this one has an empty shell, so are we good to go?
Nope.
We are actually. So we got 2 plus 2 negative. Why is this positive 2 again?
Because they have no electrons.
It gave away 2 negative charges. So if I drew beryllium now, yeah, it's number 4. And it has. Now I'm supposed to match up all my negatives for all the positives, right? So I got 2 in the first shell. So how many would I have in the outer shell? 2 more. That's those 2, but they're gone now. This is a full outer shell. This first layer, it is good to go. Alright. This is only going to make sense, I think, if you guys start doing this with me.
Nope.
Yeah. So, I printed some things off for you to
Maybe.
make it easy.
Why does it feel like a Monday?
Because it is Monday.
We'll do one together, and then you guys are going to do some on your own.
Uh-huh.
No, it's Friday.
It's like a Monday.
It's not.
Will you give that to Noah and Danielle, please?
Yeah.
Yes, Chaz to give it to us.
Paper.
Well,
Paper.
do you guys have- Danielle, can you give this pencil too when you get up there?
Okay, you can see I just copied it and pasted those Lewis dot structures out of Google Images real
Hey,
quick.
Noah.
So they're all sorts of wonky. But anyway, I want you, by the end of this, we're gonna use all of these, except helium. I shouldn't have even put helium on there again, I wasn't paying attention when I made that. I don't know that rule. But that's okay. Let's use, boron, which is just B. Which one do you think would pair nicely with boron that has 3 valence electrons? Ethan?
Fluorine.
So yeah, let's do it with fluorine, that's fine. And I'll show you sort of how this works. We have boron that has 3 valence electrons. This will start to really, hopefully, explain some things to you guys. And we have fluorine, like he said. Does anybody have out their periodic table already? Go ahead and get that out, guys, if you have it. You're gonna need it. Anyway, once you look at your periodic table, you'll see that fluorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. So how many more electrons can this fluorine accept? It has 7, so it can accept 1 more, because it wants 8. So this boron has how many to give up? Alright, so is this fluorine good now? Is it happy? Yeah, it has 8 around it. It's good. But what about boron? Is it good?
No.
With just 2 valence electrons, it's happy with that? No, it wants to get rid of all of them. So what do we need? We need more fluorine. If each one can only accept 1, fine. Thankfully, single atoms aren't just floating around through space. They're grouped up in clusters of millions and billions. So these are all going to tend to form in big bunches. We have open spots there. Now all these fluorines are good and this boron is good. So this would be BF3. Why? Because I have 1 boron and 3 fluorines. You could do them with just 1 and 2. It won't be so bad. Let's do one more together. Let's use nitrogen to start with. How many electrons does this want, Chaz? How many electrons does this want? How many more does it want? It has 5.
3.
It wants 3 more. That's right. So you see these unpaired things are like open slots. Which one on your page do you think would be a good one to pair with it?
Boron. Boron.
Oxygen.
Boron?
Yeah.
Okay.
You are. You know what? No, I think you're absolutely right. Boron. 1, 2, 3. Look at that. You said oxygen, right?
Yeah.
Chaz? Okay, oxygen and nitrogen won't form an ionic bond.
look, Hassan.
Hi, Ben. So nitrogen and oxygen won't form a ionic bond, they'll form a covalent bond, and that's what we're learning next, okay? It's a slightly different thing where instead of giving up all their electrons to something else, they share some electrons, and it's not so bad, but it's just different. It's how non-metals tend to bond. But yes, boron, nitrogen, they're a perfect match. This one wants 3, this one has 3 to give up, so this would be En. All right, I want you to try this, and I'm going to come around and see how everyone's doing. Make sure you use all of them, other than helium, at least once. That's all you have to do. Make some drawings. I'm going to come around with the video and look at your drawings with the video. But I won't look at your face or anything if that makes you feel more comfortable. So get to drawing. Please and thank you. Can I look at your guys because you guys got good starts? Nice job. Excellent. Here, I'll go ahead and put the video or the slide onto this one. So if you have your periodic table out, you can reference your periodic table and then look back at this slide to see the number of charges. You can use other elements than what I put on there too if you want. I don't care. Because you should be able to figure out how many dots to put on that Lewis dot structure.
Does this one have one? Or does this one have one? This one, right? Okay, so let's make our H, right? Hydrogen, and it has one, and it's gonna go here. So now count them for me.
Cross out this and this. You found it. 1, 2, 3, 4, 5, 6, 7, 8,
8,
9.
right? No, just 8,
Eight.
right?
That's it. Good job, Noah. Danielle, can I take a look at your work real quick with this? Because it's looking really great. Nice. Good job. Let me know if you have questions, all right?
Count with that one.
1, 2, 3, 4.
Isaiah, what you got going on? Which one are you going to do next?
Probably oxygen.
Okay, go ahead and draw that then. Draw an O with the dots. All right, so how many open slots does it have? How many more electrons does it want?
2.
2, that's right. So, not using helium. My fault for even putting it on there. Beryllium would pair nicely with it. Or you could use like 2 hydrogens or 2 lithiums. You see how we can just use the single ones to, if we just use 2 of them, we can count as 2? Yeah, either way, up to you. So you want to do beryllium with it?
Yeah.
All right.
1, 2, 3.
This way,
Yeah.
a better day. No, goddamn, nothing.
Yep. I like the arrows being drawn to it. Perfect. Yep. That's good, man. Good job. You got some more? Did you use them all? You getting there anyway? That's fine. You're doing great. How about yours? Did you use them all? You should do a harder one since you're clearly pretty good at this. I think.
Good morning, Miss Fox.
Good morning, Ben. How are you?
That's great, dude. It's coming
Okay,
through.
good. Hi, Ben.
Mr. Fox is so excited today.
Yep. I'm working on a video for my class online.
Ooh.
Yeah, I'm teaching everybody and showing everybody things. So,
Good side,
do
dude.
you want to be in the video? You want to say hi?
Yeah.
Here you go. Say hi, Ben.
Hello, Cancer.
Don't worry, it's just
You
my
upload-
professor
when
that'll
you
see it.
Upload the video in Edpuzzle, like he said it for him to watch, like of that.
Yeah, we can do something like that for sure. Oh,
I was just thinking, like, you made a video anyways.
yeah.
You can probably sit there and watch it.
How's it going over here?
I'm trying to come up with something.
I understand. Oh, those are pretty cool, like textile
Yeah,
things.
we could maybe do that, like helium.
Yeah. Yeah, I like that.
Like if you can give us one. And then I'll message Joanne to see what she has done in her other classes with her other students.
Yeah, no, that's a great idea. Using if we had more of these pink dots at least, anyway.
Yeah. Well,
Well,
I bet I might, I don't know if I have any.
if you had like 16, that would be like ideal. But I know that's not always realistic. At least 8 though. All right. No, can I take another look at yours? You're really working, aren't you?
He's trying to figure out one that's not on your paper.
That's okay. Maybe he'll figure it out. Some kids are good at this stuff, you know.
You can only use it twice.
Chaz, you got some more done. Let's take a look at it.
Can't you only use them
Nice.
like twice? Once or twice?
You can use them as many times as you want. I don't care. Just make sure you use them all at some point. TJ, yours is looking good again, man. You have any questions about it?
Yeah. For what elements do I use B and BE for?
Okay, well, let's just use one of them. Let's do BE, shall we? Go ahead and draw the BE. Okay, so let's look here. Up here, you can see that this is right here, right? That's where BE is, if you look at your periodic table. So it's going to tend to form ions with a positive 2 charge. That means it's going to tend to lose those electrons. So you can really use your imagination as far as where those might go. It's going to go to something, oxygen, for example, would be a perfect fit, okay? Because it would accept 2 electrons, and this has 2 to give. So it would just line up perfectly, BE and O. But you could also use something like fluorine that accepts 1, but you just have to use 2 fluorines. Or you can use it, like I said, any of the other ones. I mean, if you use chlorine, you draw it just like fluorine. It's going to have 7 valence electrons either way. You can use whatever you want. Alright, that's fine, but next time let's draw the arrow to like the single electrons, because like I said, I like to draw them paired up, okay? That will help us keep track of where they're going and stuff. This is not wrong. This would totally be right on a test, but just for keeping yourself straight in the future, draw those arrows to the single ones, okay?
I just don't really care where the arrows go.
I know you don't, but it's going to help you know when they're paired up, they're kind of done in a way.
I did all of them.
And that will help us next chapter too with the covalent bonding. You did all of them?
Mm-hmm.
Can I check them out with the video?